You probably already know how our modern addition algorithm works. But how was it invented in the first place? Let's explore that process of discovery and invention here on Inductica. Motivation. In our last video, we followed our new hero, Algamesh, as he invented an entirely new number system. And the thing that motivated Algamesh to make this number system is that he was tired of repeating symbols over and over again. So for example, instead of writing XXX, he simply writes 3 zeros, which means 3 in the tens place and 0 units in the ones place. This is a much more efficient number system. This system is completely superior for writing numbers. But what Algamesh does not know is whether his new system is able to add, subtract, multiply, and divide. These are methods that are absolutely critical for everyday mathematical applications, and he needs to be able to figure out these applications in his new number system. This leads Algamesh to the following question. How can I quickly do addition with my new number system? Investigation. Algamesh begins with a very simple problem. It begins with the problem 3 plus 4. In order to do this, he simply starts with 3 and then he counts upward using his fingers. He says 4, 5, 6, 7. And so he knows that 3 plus 4 is 7. It's pretty straightforward. Next, he tries something a little bit more challenging. He tries 7 plus 8. So he starts with 7 and he knows he's going to have to count up 8. 8, 9, 10, 11, 12, 13, 14, 15. He's just keeping track with his fingers and he finds that 7 plus 8 is 15. Next, he decides to add something to 15. So here's 15 plus 4. In a situation like this, he can see that this is the ones place and this is the ones place. So he should add these numbers together. It wouldn't make sense to add this number to this number. And if he adds this number to this number, that's going to give him a pretty straightforward way of finding the next one. So 6, 7, 8, 9. So once again, he's counting up, and that allows him to reach the number 19 for his answer by, again, counting upward with his fingers. Next, he wants to try adding even larger numbers. So what if both of the numbers have a number in the tens place and a number in the ones place? Well, once again, he reasons that since these units are of the same group size as these units, he can add those together. And since these units are of the same group size as these units, they're just ones, he can add those together. So what he decides to do is he decides to write them in a column. And then he'll write this line here to show that he's adding. Obviously, I'm being a little unoriginal because there's no reason to be original here. We're going to show that Algamesh is just reinventing the system we have now. So he's adding his ones together right now. He's going to start with 5 and then count up by 8. 6, 7, 8, 9, 10, 11, 12, 13. He knows what 8 looks like on his fingers, and he has counted up to 13. So he's going to write a 13 here. But then he realizes, okay, well, this 13 represents 13 ones. And so what he's going to do, he's only going to put the 3 here because this is the ones place right here. And he decides it's going to be more organized if he keeps everything all in the ones place. So he's going to take that 1, put it here, since that 1 is actually a 10, because that was 13, is 10 and 3. So he's going to put that 1 right here to be added to the tens place. And then he can simply just count upwards. So he's got 1 plus 4, 2, 3, 4, 5, okay, plus 3, 6, 7, 8. And so his final answer is 83. Now, at this point, Algamesh realizes, man, counting up every single time is going to be really, really annoying. He comes up with a way of simplifying this process. He realizes that in any one column, he's only going to ever have to add the digits 0 through 9. What he does is he comes up with a addition table. So Algamesh writes out this addition table, and this allows him to see every single combination of digits that could occur when he's adding digits. So he just writes this out on a piece of papyrus, and he keeps it next to him for whenever he has to do addition. So let's see that process one more time, this time using the addition table to kind of speed things up so we don't have to keep counting. Algamesh writes them in a column like this so that the tens are all lined up and the ones are all lined up. 3 plus 8 8. He looks at his addition table. That's 11. But of course, this is something that's in the tens place, so he's going to move that to the tens place. Okay, 1 plus 8, that's 9. 9 plus 3, that's 12. It's a 12, but this is 12 tens. 12 tens. We have 2 tens, and then we have 10 tens. Okay, well, that's 100. 10 tens is 100. He already knows that. That's just one group of 100. Oh, and it's already in the hundreds place, so there we go. And so that is the general method. This allows Algamesh to come to the following general conclusion about addition in his new system. When adding in Arabic numerals, one finds the sum of all units in each place, starting with the ones place. Use the addition tables to find each sum. If the sum in any one place exceeds 10, take the sum found in that place, put the result of the ones place of that sum in that current place, then move the group of 10 in that place to the next higher place as a single unit. Notice that an understanding of induction means that we go in an order of discovery, not just in the order of each concept, first we do addition, then subtraction, then multiplication. No, but we also go in an order of discovery when it comes to the micro level. Notice that in this process, Algamesh had to add each place value by counting first. And only once he had a reason to do so was it appropriate to come up with the addition table. And only then was he able to find out the general rule that if the sum in any one place exceeds 10, he's going to move a 1 to the next higher place. The inductive method is not just a method of science. It has implications for the proper order of education. Notice how when teaching something, it wouldn't be appropriate to teach the addition tables until a student found the need for it. If they were happy simply counting upwards, then that's fine until they see the need to quickly add larger numbers more quickly in more place values. So you can see that motivation is a key part of logical order as well, even in the practice of education. So if you'd like to join me for the next chapter in this epic inductive journey, hit subscribe or watch the next video to see Algamesh invent his own system of subtraction. This video is part of a longer series dedicated to reproving the essential ideas of math and physics by showing an actual process of observation and reasoning steps scientists could have taken to prove these conclusions. Observational proofs, also known as inductive proofs, give us a deeper, reality-based understanding of these abstract ideas and demonstrate the proper method of scientific proof. This series starts with cavemen counting rocks and will continue all the way to the frontiers of quantum and relativistic phenomena. This epic story will proceed in a possible order of discovery, since science always progresses by reasoning about observations using what has been discovered earlier. To discover the long-term goal and the true power of this project, visit my channel page for more information. To see the playlist for this series or to see my channel, just click on the links on the screen. Finally, if you'd like more lectures like this, just go to patreon.com/Inductica. For just $5 a month, you gain access to the written, rigorous forms of these proofs, as well as my 34-hour lecture series, An Inductive Summary of Physics. I'll see you in the next video as this inductive journey continues.